Hello, my name is Bruno Melo. I'm here to present my capstone project. The title is Can a GPT4-Powered AI Agent Be a Good Enough Performance Attribution Analyst? And my supervisor was Professor Jamil Shaikh. As a way of introduction, this work explores the application of AI agents within the asset management industry, specifically in fund investing and portfolio management activities. So a business process that can be enhanced by the use of AI agents is basically performance measurement and attribution. So as a way of background, performance attribution versus a benchmark is basically a technique that tries to quantify the excess return of a portfolio against this benchmark. And this is a very important part of the investment decision process. Um, and we'll see if the AI agents powered by the latest LLM models can be of use here. So our research questions are mainly two questions. You want to see if the AI agent can give in a structured data input like a report. We want to see if the agent is able to explain, interpret, and analyze the drivers of excess return with minimum error, right? And the second objective is basically to see if the agent can calculate the components of a performance attribution analysis from first principles. So instead of providing a full report like in the first objective, we want to see the all the calculations that lead to to the performance attribution numbers. Um, and before jumping into more details, I just want to mention how a performance attribution report looks like. So this is something that has many rows, many columns. The rows are basically broken down by any kind of grouping. For example, the gig sector, for example, and in here basically we have the attribution report, the attribution analysis that basically shows the effects in terms of allocation and selection in the total contribution. And that's exactly what we want the AI agent to explain, what is driving, that 38% bips, for example, on that sector, consumer staples, right? And what is driving the total portfolio excess return of 1% here, right? So to basically accomplish, these two objectives, I've explained the methodologies used. So for methodology, for objective one, which is basically the objective that wants to that basically is giving a fully calculated report, and we want the agent to explain the drivers of the attribution in that report. Basically, we created several reports that basically mimic an equity fund offering from a typical asset manager, and for that we basically have chosen a specific method called Brinson-Fazler model, which basically has the interaction effect added to the selection effect. And we also, for simplicity, we impose that the portfolio follows a long-only strategy, meaning there can be no short sellings in security. So the sum of the total weights of the portfolio and the benchmark has to be 100%. So there is no leverage. And we're going to be basically analyzing a single period and a single currency portfolio, right? And equation 4.1 gives what is mostly known as the allocation effect, which is basically given by this equation here, which in the first bracket is basically the excess weight between the portfolio, letter small w, and the capital W, which is the weight in the benchmark, times the excess return between the benchmark sector return and the total benchmark return. So from this equation, there can be several possible cases, right? So So one first case is that if allocation is positive, that basically implies that the first bracket has to be positive and the second bracket has to be positive, or the first bracket has to be negative and the second bracket has to be negative. So for the first bracket to be positive, that basically means that the portfolio sector weight is greater than the benchmark sector weight. So the portfolio is overweight that particular sector. And also means that the second term also has to be positive. So basically the benchmark sector return is greater than the overall benchmark return, meaning that the benchmark sector outperformed the overall market. So the other cases follow very similar reasoning. And we can see on the table here the combination of factors, right? So what I just described is basically this first case here, where first bracket is positive, second bracket is positive, but there is also a case where basically this first bracket is negative, second bracket is negative, meaning underweight in terms of the weight and underperformance in relation to the returns. Um, but the other one, which is highlighted in yellow, is basically when the allocation is negative, right? When you have an overweight but you have an underperformance, or you have an underweight and you have an outperformance. And the cases highlighted here in gray are basically the zero cases, right? When there is basically no allocation, the allocation is zero, which basically implies that either the weights are zero or the returns are zero. So for selection, we have an equation here highlighted in 4.4, which is basically the portfolio weight times the excess return between the portfolio, the sector portfolio return and the benchmark return. So it follows, for example, that if selection is positive, it must mean that the term in bracket has to be positive because the weight has to be positive, as highlighted before. So for that, basically we say that the portfolio sector return is greater than the benchmark sector return, or the portfolio sector outperformed the benchmark sector. So there are other cases for selection, and those are summarized in this table, similar to the one that I showed for the allocation. So and the same follows for total contribution, is basically the sum of allocation plus selection. So for the objective one, what's interesting here is basically there are several combinations of keywords, right, and values that basically have to be put together in the correct order so that the sentence makes sense. So the reasoning happens with the choices of words and values, right? So for example, in this sentence here in red, the energy sector has a positive allocation of 0.35. This was due to the portfolio being overweight in the sector, and the overweight in a sector that outperformed led to a positive result, right? So there are different combinations of keywords and numbers that have to be in the right order, or have to follow the correct reasoning, so to make it correct, right? And this is exactly what we're going to be investigating. Another thing that we use here in terms of methodology for this objective one is the use of LangChain. LangChain is a wrapper that basically gives a lot of flexibility and ready to use agents, right? We have chosen an agent called create CSV agents because we're basically passing the performance attribution as a CSV file. That agent basically is using the GPT-4 LLM as the main orchestrator of the agent. We tried with GPT 3.5, but that didn't work so well. So we stuck with the state of the art here, and we also chosen because of the choice of GPT-4, we also have chosen the OpenAI functions agent as an agent type, because that model basically was explicitly fine-tuned to detect functions and operate by instructions. I want to highlight as well the prompt. So there has been several prompt engineering aspects here as well. So pretty much we have engineered this to have two main components, right? One is the input instructions and the output instructions. So for the input instructions, we basically have tested 4 types of different prompts, right? So 3 prompts with few short learning and 1 prompt with 0 short learning. The output is pretty much the same. Let's just spend some time here on the prompt. So the instruction is basically highlighted here, that we wanted to create bullet points and to create a CSV file format, right? And the learning is basically given here below, right? I mean, the learning is basically the reasoning of the allocation and of the selection effect, right? So everything I explained before in terms of the combination of the keywords, that's pretty much sent to the LLM in the prompt, right? So for example, for few short learning, as I said, we have 3 examples. So the first one is basically this one which is highlighted here, where basically the LLM has to make a choice between positive, negative, and 0 for that numerical value. It has to make a choice in terms of overweight and underweight, in terms of of the first brackets, right? And it also has to make a choice in terms of outperformance and underperformance, in terms of the second bracket, in terms of the return comparison, right? And for selection, it's the same thing, right? So there is a choice that it has to make in terms of if the selection is positive or negative or neutral in that case, or 0, and the return whether it's outperformance or underperformance, right? And for the difference here between the few shot 1 and 2 and 3 is basically that on few shot 2, we also explain without the choice exactly what it is to be positive and negative in terms of allocation, basically highlighting those four cases of reasoning that I have showed in the table below, above. And for the few short model 3, we basically give numerical examples, right, in terms of when the allocation is positive and when it's negative, what the explanations have to be, for that to be the case, right? And the 0 shot is basically explained here in Exhibit 12. We basically don't say anything, as the name say. That there is basically no learning. We basically say, look, we just have output instructions, right? And nothing else, right? And in terms of the output instructions, basically they're the same across all the prompts, and they're basically 2, right? Descriptive texts and the CSV formats that we basically extract entities from that text, right? So the text is very descriptive, and we also extract some entities from there so that we can make evaluations later on. So later on, we're going to evaluate the text, and we're going to evaluate the keywords, right? Which is basically the entity extraction. Here is basically the keywords and the numerical values. So as I said before, the evaluation basically is going to be done on 2 instances here, right? The first one is semantic similarity, right, between the descriptive text and hard-coded sentences, using 2 methods, the Rouge and embedding similarity using cosine distance. And also the second method is basically, given that we're just going to compare, keywords and values, that's going to be like accuracy, right? So just a fraction of correct predictions, against the truth, the ground truth, right? For objective 2, remember that objective 2, we basically want the LLM, we want the agents to basically calculate, from first principles, complete performance attribution report, and we use the same reports as before, but we only show, the first 4 columns, weights, portfolio and benchmark weights, portfolio and benchmark returns, and from those 4 columns, we give on the prompt formulas, and we want the LLM, the agent, to basically calculate, a full report based on those formulas, right? And as in objective 1, we're using the same model as before, Breeson-Fessler model, and the additional nuance here is that we are introducing multi-level attribution. It uses the same principles as before, but here basically, you can make attribution calculations at any kind of level. So think about an asset allocation policy, for example, where basically you have the first level, which basically decides between equity and fixed income, and the second level basically decides which funds to invest in equity and which funds to invest in the fixed income category, right? So that's what I mean by multi-level attribution here. So the theory basically calls this macro and macro and micro. So at the macro level, you have decisions made, as I said, at the top level, and micro, basically decisions made at the lowest level, and the calculations at the micro level are similar to what we have done at objective one, and the calculations at the macro level are a bit different, but they follow the same formula. So there is not a lot of differences in terms of the formulas, as we're going to see. So for example, and in addition to have um, the agents to make this calculations in different levels, we also have a session with QA, right? Question and answer. So we basically mimic questions from actual exams, performance attribution exams, and we have two types of questions. One is a question very similar to what we see here in exhibit 18, where basically there is a report and there is a choice. So this is basically a QA/MC, question and answer multiple choice. So the LLM, the agent has to understand what the question is and go back to the table and calculate what the question is asking and return the correct answer. And another type of calculation, which I called Q-calc, which is simply a request to calculate a given effect. So instead of giving choices, we just ask calculate the attribution, the selection effects on consumer goods, for example, right? So those are the two main things on objective two, right? And here again, we use the same type of agents as before, and the prompts are a bit different, of course. We have basically two types of prompts. One called micro prompt, which is basically the one that calculates at the lowest segment level, and we have the macro prompt, which basically calculates at the highest level. So here is basically the prompts that we used. So the micro prompt basically has less formula than the macro, because that's just the way it is. But the structure of the prompts are pretty much the same. We have formulas at the top and we have instructions below, right? And just from the size, you can see that the macro requires more instructions and more formula than the macro, right? And the outputs are given in exhibit 2021 for the macro at 20. So we want to see basically two tables. The table basically showing allocation, selection, and total contribution by sector, and then by the aggregation of those sectors that we basically call cyclical and defensive. And exhibit 21 is basically the macro prompt output, right, which basically shows the output simpler. So it's basically allocation and selection by the types, right, by the lowest level types, right? And for the QA, prompts are also different. So for the QA, we have basically two types of different. The prompts are very similar, but the first prompt basically has formulas. So the structure is the same. So it has formulas and has the question. So the formulas are pretty much the same, and the questions are, of course, they're a bit different because for the first type, we have more elaborated question, basically asking what is the closest value that we are looking for, and the second one is just a question of calculate that effect, right? So there you go. And the evaluation here is it's a bit simpler than before, and it's just the accuracy, right? So we want to compare results against the ground truth, right? Obviously, we know the results of allocation and selection effects of each one of those portfolios. So it's just a question of comparing what the output is with the ground truth. And for each one of those methods, we have different results, right? So now going to the results. So for objective one, remember objective one basically wants basically to, we want to basically get the agent to reason on the drivers of the excess return sector by sector, and we used 4 different types of prompts to do that, and we basically have 2 outputs, one with a text and another one with keywords. So for the text, as said before, we are doing semantic similarity, right? And this is what I'm displaying here at the table, and so the results are as such. So the table basically showed the difference between using OpenAI and sentence transformers from Hugging Face. We see that the ranges of similarity on the OpenAI side range from 94 to 99, while from sentence transformers it ranges from 81 to 97. Comparing the prompt types, so we see that there is basically not a lot of differences, right? If we see from few-shot 1, 2, and 3, the differences are not that very relevant, right? For OpenAI and for ST, the difference is a bit bigger, but not that big, right? So there's really not big differences between that. But of course, if you compare few shot with zero shot, the difference is very significant. So basically meaning that really for for the LLM, if we want the agents to correctly reason on an attribution report, really have to have few short learning prompts. Otherwise, the results are not going to be the ones we expected. In terms of the difference between allocation and selection, we see that for OpenAI the difference is very small in terms of allocation and selection, while for ST we see a bigger difference. So we see that allocation is more accurate than selection here, right? Looking at the Rouge scores, we use the F1 score, and the results are very similar to to the ones on top. So across the score types by prompt, we see that there are no big differences as observed before. We of course we see differences in terms of few shot versus zero shot. So few shot is more accurate than zero shot, as we saw before, and we see that comparing allocation and selection, we see that selection it scores higher than allocation, especially on Rouge 2 and Rouge L, right? And this is not too surprising, given that the reasoning required on the selection is less complicated than the one required for allocation. So we see that the AI agent has this made this easier for it to basically reason than allocation, right? One thing that we notice here that we should highlight is that given the prompts, the descriptive texts are very prescriptive, and they do not deviate from the instruction we gave. That was really good for evaluating the reasoning as we saw it. So the results are great because of that uniformity, right, of outputs. However, if you want to really make this as a production agent, it cannot be that repetitive, right? So it has to have some kind of creativity on top of that, right? So one thing we should suggest is that the output can also be generated by a different LLM, right? So we have tested that with the zero shot prompt outputs, although we have seen that the results are not great, but the semantic of it, like the creativity of the sentences are very diverse, right? As we can see in this simple example here. So because it doesn't follow a prescriptive text, there are more nuances and more variations in terms of how the phrases and sentences are constructed, right? So it's just a point to keep in mind. Now going to to the second method, where basically we check the accuracy of the keywords, right? So looking at the table, basically, and so before we have basically two different types of accuracy. One in terms of numerical values, as we call it, the value column here, and in terms of the keywords. So outperformance, underperformance, overweight, underweight. So for allocation, we basically have three different effects to evaluate. For selection, we only have two, and we see that um, um, there are several conclusions we can take it from here, right? So first of all, few shot learning versus zero shot learning. So in general, few shot it's it scores higher than the zero shot, as highlighted before. Another interesting conclusion here is that looking at the different few shot results, the difference is not that big, although we see here for the allocation, for example, a variation of 5 points, for example, here on the sector performance. But on the selection, the variation is like 2% only. But there's not a lot of big differences, right? In general terms, right? So, but comparing, specifically allocation and selection, we see that the scores on the selection side are higher than the allocation side, and this is basically the same conclusion as we saw before. That the agent. This is much easier for the agent to reason, right? The selection effect is much easier for the agent to reason because he only needs one word, one combination of word, right? On allocation, there are two combinations, and that basically shows it in the performance, right? So we basically see that here, right? Sector performance versus sector weight. So we see that there is some kind of struggle here on this side for both few shot and zero shot. And we think that we could find a way to basically reduce that error, and we're going to show that a bit later on. But yeah, so one way that we think that we can reduce that error here in terms of the sector performance is basically to have a dynamic evaluation feedback. So following here the boxes, right? So the idea is that when basically there is when we do the evaluation phase, if that evaluation is wrong, we just feed back to the prompt with another prompt, basically saying that the previous prompt was wrong, that the agent has to redo the calculations and redo the reasoning, and that can be done using memory, right? So we haven't explored the use of memory in the agent. LangChain gives that optionality in the function, but we haven't used that. So that could be a very interesting way to use memory here, basically to feed back to the model, to the agent, without giving the right answer, but basically just pointing out that that it was wrong, and try to have and try to run it again, right? And just stop it when it's ready, right? So I think this is a very cost-effective way of reducing that inaccuracy, right? Because we have seen from here, the accuracy is already very high. So I think one, two or three other loops until we get the final answer, it shouldn't be too expensive, right? And in this in this process here, we also show what we have discussed before, the sentence generation, right? So given that the sentence generation is very repetitive, we should have a process here that basically creates more more variations in terms of sentence, right? And that is basically fed back into the prompt, so that the agent can basically create sentences with the correct reasoning and going through the evaluation process before before there is a right answer, right? So this is um, um, one of the things that we are um, giving um, um, as one of the takeaways from from the work here. Yeah, moving on to objective two. So something I forgot to mention on objective one is that GPT-4 didn't have any big issues to basically run the calculations over there. However, for objective two, we did experience issues, especially when we had to produce numerical results on the macro level calculations, right? And in some of the question answers, but the trouble that we had more was at the macro level calculations, right? On the micro level, we see that everything went very smooth, but at the macro level, and we suspect that because the prompt is very is big and it's very complicated, you could have hallucinated in some of the in some of the instructions there, and of course, you know, the result, we're going to see that the results are still very good, but we had to run it several times to get the right result, right? But let's get to there to that in time. So method one, multi-level attribution report. So for micro level calculations, so accuracy is 100%. So we didn't have any issues here, and the agent ran it, one time for all the portfolios, for all the sectors, and we had 100% accuracy. So it's a very, very good result. But as I said before, for the macro level calculations, although we are able to get perfect accuracy in the end, as the table shows, we had experienced problems, especially on we named our portfolios portfolio growth and portfolio value. We had issues specific on those two portfolios, right? So this is a table that basically shows one of the runs that we had before that basically shows a very low type of accuracy because of several errors that we found during the runtime. Although we are able to reprocess and have it right, that is far from perfect, right? It shows that there is it doesn't like so much the prompt, right? So you have to run it several times until you get the final the correct answer. So that shows that there is something going on in the background that it's not very optimized, right? So it's one of the things that we leave it for future work, just basically to see if that macro prompt can be optimized, so that in the end, because we see that in the end the results are very good. You can calculate at a very high level of accuracy very complicated attribution analysis, but it's just that it takes several tries, right? And on a production system that shouldn't happen at all, right? So that has to be investigated further, right? But one thing that we highlight is that given the level of complexity in that prompt, and given the level of complexity of that calculations, we're very impressed with GPT-4 here, and we tried GPT 3.5 and wasn't able to do it. So we really think that with GPT-4 and more complex models in the future, we can really extend the calculations to geometrical returns, multi-period, multi-currency, and include fixed income, which is a bit more complicated than equity, and derivatives, short positionings, all those kind of complications. I think a model like GPT-4 or a higher model could would be able to to calculate those calculations, those results as well. Second method, which is basically the question answer, we ran 140 questions, 70 on what we called QAMC, question answer multiple choice, and 7 questions which we called QCalc, which is basically the questions with a specific command to calculate an effect for a specific sector. And accuracies are given in the table below. So accuracies are very high. So for the multiple choice, accuracy is close to 90%, and the calculation, the pure calculation, the accuracy is close to 85%. We believe that with those types of accuracies, an agent like this would be able to to pass an exam, right? An exam that requires that kind of that calculation. And the only trouble we found here was on the 140 questions, just one answer didn't come out as we requested. So the output was very specific to basically answer with a letter or answer with a numerical value. And in one of them, it gave something like this, right? Given the calculated allocation effect, the closest value is D. So it basically described the whole thing instead of just coming up with either the letter or the number, right? But this is just one in 140, right? So in conclusion, the main hypothesis was that that we want to see if an AI agent, powered by a state-of-the-art LLM, would be could be used for as a performance attribution analyst, right? And we think yes, it can. So the conclusion is that the research is successful, right? So basically, we show that it's able to produce an analysis, right, in terms of reasoning on the drivers of excess return, and also is able to calculate components, right? I mean, very complicated components, even at a multi-level type of calculation, right? So we are very happy with the results. We think there is a very clear signal here that this field of performance attribution analysis and investment performance, it's really ready to be disrupted, right? So there is a lot of other research that can be done here. As we point out, we could test other LLMs, maybe smaller LLMs or combination of LLMs to do the several types of calculations that we did. We could test different type of prompts, for example. As one of the takeaways, we presented a dynamic evaluation feedback loop process. That basically would require changes to the agent Python class. Something that we didn't do. We just used something from LangChain directly. But that's something that could be investigated. We also could use knowledge graph basically to ground the analysis as a knowledge graph and see if the results would be different. And last but not least, basically expand the scope of the performance attribution, right? So we basically used a very simple equity portfolio with no derivatives, no leverage, no short selling, and single period, single currency, and we can basically try to expand that to a multi-period, multi-currency, and also investigate other asset classes like fixed income, which is much more complicated than equity, which only has two effects, right? Allocation and selection, right? But that's it for my paper. Thank you very much, and see you soon.